Welcome, everyone. Thank you for being here. Thank you for being in person. Thank you for coming to the live stream. This is pretty amazing. What do you guys think of the venue? Pretty cool, right? Whew. I'm surrounded by 3 bars. How cool is that? So thank you again. This is great. Thank you for your contributions. Thank you for being part of the community. You can see some of the names of the folks represented here behind me, if you guys can see that. It's actually pretty amazing. It covers academia, industry, startups, developers. Lots of independent developers are here. So it's not the C-suite, not the executives. It's the real core of the community. So we're so excited. So let's talk briefly about what we're going to talk about today. We've got a kind of an interesting lineup. We kind of sit at the intersection of research, open source, engineering. And it's not your usual conference. We're not going to have long talks about science. We're not going to talk all about code. We'll actually have talks that kind of blend the 3. So first off, we're going to talk about PyTorch 1, so have the core team come up. So these are the core developers. They span FAIR, as well as the AI infrastructure team. We will jump into research. So Jitendra Malik is here, kind of a rock star in the field. So he'll talk about research and how we use PyTorch. Bill Jha will talk about production at Facebook. We use a hell of a lot of PyTorch. We'll then go into lunch. After lunch, we have great representation from the cloud providers. All the major guys are here talking about how they're enabling PyTorch in their clouds, developer tools, some surprises as well. We'll jump into academia. So we have some of the top universities, Caltech, NYU, UC Berkeley, some great speakers. Enterprise labs, how they're applying PyTorch for their research, and then taking that into production. And then we finish up with education. We have Fast.ai and we have Udacity, both speaking on how they're scaling their curricula for their students using PyTorch. And then lastly, we have a panel, which is really made up of some of the top minds and kind of thought leaders in the space. Chris Latner from Google's here, Noah Goodman from Stanford Uber, Yanqing Jia from Facebook, and then Jeremy Howard from Fast.ai, and we'll talk about the future of AI and software. And then hopefully everyone sticks around for the poster session, which is going to be out here. There's whiteboards, if anyone has the desire to do a little bit of whiteboarding with everyone. And then happy hour, of course. Let's grab a glass of wine and beer afterwards and hang out. And so to kick us off, I'm going to hand it off to Facebook's VP of AI, Jerome Pacenti, and the guy who signs my checks. So be nice to him. Thank you.
So it's pretty amazing that a project that started just 2 years ago by a handful of engineers actually managed to create in such a short time a really rich and vibrant community. So today, actually, you'll hear from research scientists from industry and academia. You'll hear from engineers that are using AI to scale and to create new applications. You'll hear from cloud platforms, Azure, AWS, Google Cloud. You'll hear from tool builders who are providing new systems to the PyTorch environment. And then you'll hear from education providers who are teaching machine learning and deep learning with PyTorch. Now, before I go into PyTorch and tell you a lot about AI development, let me tell you why really PyTorch and AI matters to Facebook. So 5 years ago, we started actually the AI team at Facebook. And in 5 years, AI has become really an integral part of everything we do at Facebook. One thing is that we use AI to enhance our products. So if you go on Facebook, you ask for a recommendation, the system uses NLP to identify that, and text your friends' comments and put them on an app. We use automated machine translation to allow people from hundreds of different languages to communicate and understand each other. We use computer vision to help people with vision impairment understand what images and videos are about on our platform. We also use AI to really power new experiences. So we use AI to create hundreds of thousands of bots on the Messenger platform. We use AI to analyze the videos that are uploaded on Facebook Watch to create automated thumbnails and trailers. We use AI to power all the augmented reality effects that are in our apps, as well as our virtual reality hardware. We also use AI to protect the community, to try to understand the content that's uploaded to a platform and minimize the bad content, harmful content, by flagging it and removing it. We also use AI to identify people in need and make sure they receive help. But even more than that, AI powers the key system within Facebook. When you go to Instagram or Newsfeed, there is a powerful machine learning algorithm using deep learning that determines what content may interest you most. So Facebook is really one of the key and major users of AI in the world today. And it's in our interest, actually, to make AI progress as quickly as possible. And we believe like, the key to making that happen is to create a community around AI that's open and collaborative. We'll also create a research group that creates partnership with other academic research groups. We have more than a dozen partnerships with universities around the world for research. All this to ensure that AI is really advancing quickly and making progress that is shared among the community. Facebook itself is really a provider of this research and improvement in AI, and I'll give you a couple of examples of things that we have done in the past year. One system is around image analysis and video analysis. So 6 years ago, ImageNet was kind of the task that put deep learning on the map, that showed that deep learning systems were really competitive for image recognition tasks. 6 years later, image recognition has passed human performance. But more importantly, we're able to create systems that analyze images to a really much more refined level. So here I show a dense pose. It's able to, just on a mobile, analyze a video in real time and extract the surface of the body in motion. We also created a really interesting machine translation system that we announced just a few months ago that's able to look at 2 different languages independently and without any example of translation, figure out how to do a translation from one language to the other by mapping the concept and putting them together. Now, what the key problem in my team is, how do we take this research and move it to production as quickly as possible? The 2 systems that I showed today have been developed this year, and it will take us a couple of months to put them in production. But what if we could do that just in a matter of weeks or even a matter of days? Okay? So this is really the impetus behind PyTorch 1.0. Let me tell you a little bit how actually it used to work at Facebook. So the research to production framework process used to involve 3 different frameworks. The first one was PyTorch, which was developed for research. It's a flexible framework. It's easy to use. It uses a Python-first design, an imperative front end, really something that researchers and people exploring new models love to use. Okay? But the standard model was for the models created by PyTorch to be ported using Onyx to a more suitable framework for production. And at Facebook, that framework was Caffe 2, which was really the workhorse of our production systems. Very robust, optimized for scale, deploying all our data centers in a billion-plus mobile phone. And I was pouring today more than 300 trillion predictions a day. But the question is, could we take these 3 different frameworks and put them all in one? And that was the impetus behind what we call today PyTorch 1.0. A framework that allows you to do seamless transition from AI research to production. Now, you're going to hear a lot about PyTorch 1.0 today from the team that has developed it. But let me tell you a little bit about the challenges that we solve with PyTorch 1.0. The first one is we wanted to make sure that people could write code once and not have to rewrite it or re-optimize the code to go from research to production. The second is we want to make sure that you had performance throughout, especially for large data set that need a lot of computing that's distributed. The third challenge is we wanted to make sure that not only you could use PyTorch, which is great for prototyping, but for other use cases, you can use different language more adapted to more performance. And finally, we wanted to make sure that people could use PyTorch, deploy it at scale really, really, really easily. So you'll hear more about that today. But before we get there, I'd like to tell you a little bit also about the future of this. Right? I've been in AI, and I've been in software development for now more than 20 years. And when I started, I remember the way of working was you had to start developers, and I've done that, writing 10,000 lines of code without a single line of test. Okay? Now, in the past 20 years, the industry has learned to create much more robust software. We have developed best practices, some toolings, our environment to make sure that we create software that's of high quality. I kind of believe that machine learning engineering is where we were in software engineering 20 years ago. So there's a lot of things still need to be invented. We need to figure out what testing means, what continuous deployment means. We need to develop the tools and environments so that people can develop robust machine learning that doesn't have too many biases and doesn't overfit. I also believe that the world has changed, and the days where the development of hardware and software are separated is no longer the case. We have such needs for such high needs for compute power that it makes economic sense right now to develop specific hardware for specific machine learning workloads. So that's going to be a different thing today. Now, as we say at Facebook, this journey is just 1% finished, okay? And as we go on that journey, we at Facebook and in PyTorch team believe that we need to satisfy 3 core tenets, right? We want to develop a system that really puts the user at the center, a system that developers and researchers love to actually use, and that's very intuitive. We also really believe in the community. We want PyTorch to continue to develop organically through community projects, through community contribution, and through community events. And we also don't believe in a monolithic framework. We believe that the kind of unique style system where you have a lot of components who work well together and let the developer and researcher figure out what they want to use, okay? Now, today is really about you, and it's about this community. And I hope that you really enjoy hearing from a lot of people from that community, and it will really get you excited to participate to it. Thank you. And for the next session, I'll introduce Sumit. If you don't know Sumit, go talk to him. He's really the spirit behind PyTorch, and he'll tell you more about all the good things in PyTorch 1.0. Thank you.
Hey guys. How's it going? Man, this is incredible. It's just incredible to see all of you come here. Unbelievable. And I was just catching up in the morning with a bunch of you. You came from 12-hour flights. I'm still, it's sinking in, all right? I need to do my talk as well. So one thing, I'm going to start the deep dives. I'm going to introduce what 1.0 gives you, and I'm going to hand it off to Dimitro and Zach and Peter and Tang, who are going to do further deep dives. So to do a quick look back on 1.0, something that if you start from the first public release, which was 0.1.12, every single release since then, we introduced 1 or 2 major features that you guys really, really wanted. Either you gave us direct feedback, or we also were users as well, so we realized certain things were missing. So with 0.2, we introduced distributed PyTorch, so you can do multi-machine training. And then we also introduced more Pythonic concepts like broadcasting, advanced indexing. And we also introduced higher order gradients, which have been pretty essential for a bunch of recent deep learning research. And in 0.3, one of the things that a bunch of you have asked us was, hey, we're actually doing really small NLP CPU models, and your framework overhead is really high compared to a framework like Dynet. Do something about it. So we actually spent a solid 3-4 months optimizing our framework overhead, reducing just the framework overhead itself by quite a lot. And we also introduced Onyx support because, as Jerome said, it was our first critical step towards gearing up PyTorch to production. We developed our internals to make sure we can start emitting Onyx IR, and that was when we started also shipping PyTorch models to production at Facebook. And in 0.4, thanks to Peter JC123, our awesome GitHub contributor, who couldn't be here today, we added Windows support, and then we added more engineering to make sure it's robust and shippable. And the other thing we did, one of our biggest API changes that we introduced since release, was we merged tensors and variables, and no one has told me they were unhappy with that change. I think it just got rid of so much boilerplate code, and PyTorch code since has been in a much happier state. So in 1.0, something we are doing is we are investing in like future needs, both on the production side and also to take care of the changing deep learning landscape. So in 1.0, we're announcing the introduction of torch.jit. It's the PyTorch's JIT compiler. It's a very high-level compiler. I'll tell you why we're doing this investment, what significance it brings. So if you think about PyTorch, in PyTorch, your model is code. You write a Python program, and that itself is your neural network, and there's no real difference. Now, one of the downsides of that is that you can't really manipulate your model or even export your model to another runtime that can run it. Because your model itself is Python code, you need an entire Python VM to be able to run your model if you exported it. So with torch.jit, we're introducing a couple of concepts. One of them I'm going to briefly show as an example, and Zach will deep dive into the whole torch.jit later. What we're doing is we're starting to add function and class annotations where you can, if you just have your code, and that's just standard Torch code, and you add a function annotation or you do tracing, that code can then be inspectable and exportable. It effectively transforms into our high-level intermediate representation that you can save to disk or execute in our C++ only runtime. And this is very, very important for whenever you talk about deploying PyTorch, whether deploying PyTorch for production, or you want to deploy it to embedded systems, or if you want to deploy it into a large code stack that doesn't want Python in the way, which I think a lot of you have given us feedback about as well. So one need is addressed is production deployment, and that is something Torch.jit did as well. The other thing that we wanted to invest in, again with Torch.jit, is that we want to, as hardware is getting faster and faster, I mean, we had good NVIDIA GPUs, Maxwell, Pascal, and then we have Volta, which is so much faster than Pascal, especially in FP16. And then we have TPUs, and we have so many other hardware. We have GraphCore, Cerebras, all these hardware that's coming out. And all of them are getting faster and faster. And if you run code imperatively, like one line at a time, there's a lot of optimizations you leave on the table that actually start mattering. So one thing that the JIT can do once you add the annotation is it can actually inspect things ahead of time. It can actually look at your whole program and then try to find fusion opportunities, try to make things faster or more memory efficient. And that's very important as it does these code transformations and tries to like fuse a bunch of graph nodes together on the fly, not an offline process, but like as it runs the code, it figures out it needs to like generate new code. This gets more and more important, as I said, as new hardware comes through. And whole program optimizations in just like small anecdotal evidence, like I've seen it matter like 10, 15, 20, 30% in speedups on like larger whole programs. So I think it's honestly a good idea. Like as a PyTorch team, we think investing in a JIT for both production needs and for the future hardware needs as hardware gets faster and faster, it's really important. One of the important things I want to point out is 1.0 is not a small number. It's not an easy number to say, I'm saying, oh, I want to ship 1.0. Of course, I can call it 3.0 as well. But like from 0.4, which was a pre-release, to 1.0, which is what we generally consider a very stable and mature release, we need certain characteristics for what we ship. And some of those are like, we want to make sure people can rely on 1.0 for their critical deployments, for their critical research. They don't want like nasty bugs appearing here and there. I mean, we had those times in 0.1, like pre-release, and like a few bugs here and there. But at 1.0, we really want to make sure we tighten things up. So today, we are releasing PyTorch 1.0 preview, which is basically a release candidate build. It has 90% of the features that you expect to have in the 1.0 stable build. And it's available for download today. If you go on the website, you can click on the preview button. It's basically not a separate branch. It's just the nightly build. And we actually, I'm serious about 1.0 preview being fairly stable already. We run this in production ourselves. We run the top of the stack master commit at production, and we use it for research every day. So it's not, just because of preview, it's not really unstable. It's actually fairly reasonably in a good shape. So try it. The other thing that Peter will be diving into later in a few minutes, actually, is that we will also be shipping 1.0 with a C++ only front end. That's also available for download with precompiled binaries, and it's the libtorch button that's there. And I'm kind of excited for all of you to try it. Give us feedback. Please do so, or else we can't really improve the process. And 1.0 is the first step to making sure PyTorch is production scale and production ready. If you don't have particular features, don't get disappointed. They will come as we progress PyTorch into a more production-friendly environment while making research the central, and research and flexibility the central component itself. So I'm going to hand it off to Dmitro, who is going to talk a little bit about what's coming in PyTorch production, not just in the current release, but also in the next release. And 1.0 stable, by the way, is going to come somewhere before NIPS 2018. I know end of summer wasn't really the best date we gave for the 1.0 preview, but before NIPS 2018 starts, we're going to have 1.0 stable, committed, and shipped to PyPy and Conda. Off to Dmitro now. See you guys.
Hello, everyone. My name is Dmitro. I work on PyTorch and broader Facebook deep learning platform. And today I'm going to talk about production challenges and some of the technologies that PyTorch 1 has to address them. PyTorch already established itself as a very flexible modeling environment for prototyping and research. However, when you have your idea working, scaling it up to a larger data set or shipping it to tricky deployment environment is often a hassle. Our goal with PyTorch 1 is to expose the high-performance building tools for optimizing your model and do it through the same familiar PyTorch product programming environment. I want to highlight that this functionality is fully opt-in, so you can still use your regular PyTorch API for experimentation and basically go through the necessary refactoring and tweaking steps only for the part of the model which you need to get perf improvements from or which you want to deploy. And our goal is to make this process as seamless as possible. So what does bringing to production can actually mean? There are multiple constraints which production systems usually pose on your programs. One of them is hardware efficiency, because in many environments you have very tight latency constraints. And also, just when you're running on really huge scale of hundreds of thousands of servers, even small performance regression can basically increase your cost dramatically. Scalability usually means scaling to a much larger data sets with billions of images or hundreds of billions of training rows, and also scaling to multiple millions of simultaneous requests in inference. And there are, of course, all the platform constraints imposed by the broader context in which neural network models are running in. For example, in some cases like embedded devices or robotics, there are pretty tight constraints in what's possible or what's not possible to deploy. Luckily, we are not starting from scratch. As you probably know, in Facebook, in the past several years, we developed Caffe2 deep learning framework, which focuses on uncompromising performance and all the necessary tools to achieve it. We used Caffe2 backend for several years to support all Facebook production deep learning needs. from data center to several billion, to like more than a billion of mobile devices. We are viewing PyTorch 1 as an evolution, which brings all these components and best practices which we learned through production use cases to the same familiar PyTorch frontend, and basically bringing the same experience to our deployment world. So let's take a look at some of the features which are part of PyTorch 1, and also some of the stuff which is in the works and is going to be coming in the future releases. So first of all, when you're running on hundreds of thousands of servers, you don't want to leave any performance on the table. From the beginning, PyTorch uses best vendor libraries such as QDNN and MKLDNN, and we are improving those integrations. We also invested a lot of effort in improving basic core library performance. So even simple tensor operations like reductions and strided tensor performance, expect them to run faster. And going forward, we are basically, as we integrate more kernels from Cafe 2 into PyTorch environment, operator library basically becomes more beefed up and running faster on many cases. Getting the best performance out of hardware often requires optimizing not only a single operator, but also chunks of the graph, basically multi-operator pieces of the program. For example, it's necessary if you are trying to do some kind of fusion, or if you're trying to change the tensor layout for a bigger part of your model. Of course, nobody can optimize for target platforms better than hardware vendors themselves. And that's why last year we started and basically co-created Onyx initiative, which is targeting this kind of standard model exchange format. So different hardware-accelerated runtimes, such as NVIDIA TensorRT or Glow, can be plugged in the broader frameworks. PyTorch already supports Onyx export natively. And going forward, we're also making it easier to accelerate only a chunk of the model in the broader context without having to export the entire model. And that's coming in the future releases. When you're trying to scale to production-level datasets with billions of images, it often becomes challenging. Running on hundreds of GPUs is not easy and requires high reliability. And also, production clusters often have like heterogeneous nodes or mixed networking stacks and stuff like that. In PyTorch 1, we basically fully revamped distributed backend, and Tank later on is going to talk about it in more details. Well, there is Py in PyTorch, and Python is great as an environment for prototyping. And even if you're doing large-scale training, it often works just fine if your kind of compute blocks in the model are beefy enough. But overheads of Python interpreter, especially like global interpreter lock, are often a showstopper for small models, whether this overhead is higher, or if you're trying to run in your target application with multiple threads and multiple models running on the same machines. Also, in some environments, such as robotics or on mobile deployments, often running Python interpreter is just not an option. With PyTorch 1 and TorchJIT compiler, we basically build in tools to extract only part of your model, which is necessary for production deployment, and export it into serializable representation, which can run on a very small embeddable C++ only runtime, which can be embedded in your target application. All you need to do is basically export your model, link it to your application with libtorch.so, and utilize simple C++ API to load your model and execute. So we covered a few topics. Let's now talk about some of the stuff which is going to be coming in the future releases of PyTorch. In order to run efficiently on modern hardware, it's often necessary to utilize lower precision computations. The thing is like 16-bit or 8-bit or even lower precision arithmetics takes much less space on the chip and thus far takes less energy and achieves better computational throughput. With the right tricks, it turns out you can actually train and do inference of your models without losing much of the accuracy. In fact, we saw basically gains of several X from quantizing some models in Facebook environments to int8, and without substantial accuracy drop. We are going to open source some of the libraries for efficient int8 compute for both server and mobile side later this fall. And also going forward in the future releases after 1.0, we are working on smoothly integrating these quantized compute routines inside the PyTorch frontend, as well as giving you like recipes for quantizing existing models. This functionality is going to be available soon. And of course, in some cases, you need to run models on the mobile devices, either for privacy or performance constraints. That's not easy, and it's often challenging, and there are multiple reasons for that. First of all, there is no single mobile platform. You basically have to deal with two major operating systems, something like 24 of different chipset versions in CPU architectures, and several compute APIs. Also, mobile devices often have like very hard constraints in terms of code size and model size, and also energy consumptions of your model. As you probably heard earlier, at Facebook, we developed lightweight Cafe2Go mobile engine that ships and runs on more than 1 billion mobile phones. And you can use this engine today by going through Onyx Export to bring your model entirely. And going forward, after 1.0, we're basically going to integrate some of the functionality of taking your model and kind of applying necessary tricks to compress it for the mobile deployment as a part of the same PyTorch APIs. So just to summarize, PyTorch 1.0 comes with core features which will address your deployment needs. But it's only the beginning of the journey, and we are basically committed to provide smoothest experience for bridging research and production gap, and expose all the performance components which we kind of built and learned over the years through the same familiar PyTorch interface. Of course, as Sumit mentioned, many of these techniques basically require optimization of the larger chunks of the model, and basically being able to analyze the model structure programmatically and apply some of the automatic recipes. Our approach is to capture structure of your PyTorch model with minimal changes to your source code. That's basically the goal of TorchJIT, and to make this process seamless. And this, I'm handing over to Zach, who is going to talk about TorchJIT in more details and walk you through how exactly it works. Thank you.
Hi, and thank you, Dima. I'm going to talk about how we can transition models from research into production using PyTorch's JIT compiler. So when we started and we released PyTorch, we found that people really loved PyTorch's eager execution model. Basically, your model is just native Python code, and AutoGrad allows you to take a derivative of whatever code you need to run to calculate and optimize your models. Because everything is just native Python, all of your favorite debugging tools, like printing things out, or GDB, or other visualization tools, just work out of the box. And if you wanted to use an obscure Python library in the middle of your model, there's absolutely no friction to doing so. And in truth, I think a lot of the fundamental new models actually start this way, with crazy, hacky prototypes that glue together different Python libraries with NumPy and various other things. And we really, really like this workflow. It's been great for prototyping models, for trying out new things. But once you've got a new thing you really like, these small amount of models that you actually want to run efficiently need to be deployed. And for this, this Python eager workflow has some issues. In particular, the models are really closely coupled with Python. The Python interpreter needs to be present in order to run the model. And this really isn't convenient or possible to always do, especially true on mobile devices where you really can't ship the Python interpreter, but even on servers where you want good multi-threaded performance and you're worried about the global interpreter lock. And furthermore, in addition to not wanting to have Python around, all the dynamic features of the Python language make it really hard to actually run programs efficiently and optimize them. For instance, it's really difficult in just Python alone to perform operator fusion or do algebraic simplification. So to address these issues in PyTorch, we built another way to express PyTorch programs that allows them to be run independently from Python. Just to be clear, we really like PyTorch as today. And so the version of PyTorch you use today is going to exist unchanged, and we'll start to refer to this as the eager mode of the PyTorch runtime. But in addition to this eager mode, we've added a script mode to the PyTorch runtime. In this mode, models are expressed as an optimizable subset of Python that we can run without the Python interpreter. This subset contains all the building blocks necessary to build models, tensors and fundamental operators like matrix multiply and convolution, traditional language features like if statements and loops. But it restricts the dynamic behaviors in Python that actually make it difficult to optimize. Because we believe in the flexibility of the eager mode for prototyping, we expect that most users are going to first write whole programs in that form, do a lot of experiments, train models, figure out what actually works. But for the small subset of successful models that you actually want to put into production, or where you actually need a lot more performance, the PyTorch JIT provides tools for taking code originally written in this eager mode and annotating it so it's possible to run it in script mode. And these tools we provide allow this transition to happen gradually. This means function by function and module by module. We think this is hybrid use of these runtimes is important because it allows you to incrementally make changes and check that nothing has been broken before continuing. And if, for instance, you need to go back and do some more prototyping on your model, nothing stops you from going back to eager mode for a part of the model to do that experimentation. So to actually do this transition, the JIT offers two techniques, which I'll go into in more detail, one based on tracing and one based on scripting. For straight-line models where there's no control flow, like a computer vision model, we allow you to trace the eager execution of your model, turning the trace of what was executed into a TorchScript program. This allows you to reuse existing eager mode code with very little changes to your module code. For instance, here we have an example. We have a simple function written in eager mode called foo. We can call torch.jit.trace on it, providing example inputs for this function. Our tracer infrastructure then runs this code, recording what tensor operators have actually occurred, and then it records this trace into a straight-line TorchScript program that's then returned as a new thing called trace.foo. This trace.foo can run independently from Python, and as we'll see later, you can save it to disk and load it without Python present. This process works for larger models as well. For example, in a second example here, we take the ResNet model from Torch Vision, run it with an example image, and that turns into a self-contained TorchScript module that includes all the forward code for ResNet, as well as all the module parameters needed in a self-contained bundle. So when working with tracing, it's important to realize that tracing actually just runs your model as is, recording what's executed. It doesn't record any of the Python control flow in your model. So while it's great for vision networks that are pretty much straight lines of code, it doesn't work for custom RNNs or any other code that contains if statements or loops. For models where control flow is important, like a custom RNN, we allow you to directly write code in TorchScript using a subset of Python. In this subset, you mark functions with a script annotation to denote which should be compiled into TorchScript. Because it's an annotation, control flow is preserved as written. So for instance, here we have this RNN example, which is expressed as a script module, which is like the equivalent of a normal torch nn.module. Parameter initialization code is exactly the same as normal PyTorch models, but the forward method of this model has a script method annotation that turns the model into a TorchScript method. You notice that this model has a loop in the middle of it. That loop is preserved as is, and we even allow you to write print statements in there to actually debug your code. It's important to remember that TorchScript itself is a subset of Python. You don't have to learn a new language, and I think more importantly, if something isn't working for you and you want to debug further, you can remove the annotation, and the function will execute as normal Python, enabling you to use whatever debugging workflow you're familiar with. Unlike graph building frameworks like Caffe2 or TensorFlow, this mode still has you directly writing a program in a programming language, not meta-programming the construction of a graph. So models still read like traditional programs and are much more one-to-one with PyTorch's eager mode as it is today. And finally, we allow you to mix and match eager mode code with tracing and writing script functions incrementally. This allows you to gradually move your model over to script while checking you haven't broken anything. And it also allows you to use the right tool for transitioning models for the job. You can use tracing for the straight line pieces of your code and only use scripting when you need control flow, for instance. Once you have a model fully converted into TorchScript, you can then save it to disk as a self-contained archive. The archive that you save, like in this example code here, contains all the code for your model and all the trained weights needed to actually run the model. Once saved, you can load this into a separate process using our C++ API. Peter will talk more about the details of this API later. But the API itself uses the same PyTorch kernels and libraries that exist in Python today, but is carefully factored so we don't have any dependencies on Python, making it suitable for server deployment. I want to point out today that in our preview release, TorchScript supports a small but usable subset of Python. You can use tensors and numeric primitives, if statements, simple loops. You can organize code into modules, use tuples and lists, print and strings, and you can calculate gradients that propagate through script functions. However, we don't support all of the features of Python, and there are a few important features of PyTorch that we don't support yet that you should be aware of when trying it out. In-place updates to tensors or lists don't work yet. Direct use of existing modules like conv doesn't work directly in script. However, you can trace a conv and then put the traced module into a script, and until we support the direct use, we suggest you do it that way. And finally, you can't call grad or backwards directly in a script function, though you could put them outside of script functions and calculate gradients through them. For these three limitations here, we want to be clear that we want to actually support these, we just haven't had time to finish them yet, and our plan is to have these features coming in the 1.0 stable release that will happen in a few months. Furthermore, we know it's important for you to be able to understand what you can and can't use in the script front end, so we've put more details in our documentation online that walks you through what you can and can't use. Preview builds of PyTorch today are available that contain this JIT functionality. We've posted new tutorials describing in detail how you use it and more documentation about the APIs. I'll now hand it over to Peter, who's going to tell you more about the C++ APIs I previewed earlier. Thank you.
All right, hi everyone. Thank you very much. I'm Peter, and I'm going to tell you about the PyTorch C++ API, which provides flexibility, simplicity, and performance across language boundaries. So you just heard a great deal about how PyTorch 1.0 enables new pathways, whether it is the path from research to production or from eager PyTorch to TorchScript. But another path we care very much about is the path from Python to C++ and from C++ back to Python. And the reason for this is that we realize that Python is not always the optimal solution to the problems PyTorch users face, and that sometimes you just have to go all the way down to a language as bare metal as C++. And we want to be able to provide you all with all the support and all the options to use PyTorch even in such environments. So you already just saw an example of loading a TorchScript module in C++ for production and inference purposes. And you may already have been asking yourself, what if I need to extend my script module with a custom C++ or CUDA operation? And we'll answer that question in just a second. First, let me give you a bit of a brief overview of what we mean with the PyTorch C++ API. So at the foundation of PyTorch lies a high-performance CPU and GPU-enabled tensor library called A10. You can see examples of creating and manipulating tensors with A10 on the right. Built on top, the PyTorch AutoGrad augments A10 with the notion of gradients and differentiability. This means our tensors can now require gradients, and we can call .backward to initiate reverse mode automatic differentiation. Now, the exciting news is that A10 and the AutoGrad not only form the foundation for PyTorch, but we also provide first-class C++ APIs for you to leverage these two libraries to extend eager PyTorch and TorchScript with custom functionality. So if you wanted to write a custom C++ operation, you would usually want to start by extending your eager PyTorch model for research and experimentation. For this, we released C++ extensions earlier this year, which provide you a way to bind a C++ or CUDA function into Python for use with PyTorch. And then, on your path from research to production, you would, of course, want to transition this C++ operation also to TorchScript. And for this, we provide a mechanism called TorchScript custom operators, which provide the same flexibility for your TorchScript models. And we'll dive deeper into those in a second. First, let's take a look at C++ extensions. One use case where C++ extensions really shine is when you want to call into a third-party C++ library, like OpenCV. So here's a minimal example of writing a C++ extension to call the warp perspective function from OpenCV, which PyTorch does not provide out of the box. Here we include the torch extension header, and then define a small function which accepts and returns A10 tensors, converts those tensors to OpenCV matrices without copying any data, then calls the warp perspective function, and ultimately returns the result as a new A10 tensor. And to then bind the C++ function into Python, all you need to do is write 3 lines of binding code using py-11, where you specify the name and the address of the function. And this will create a Python module that exposes your C++ function as a Python function. Now, you may be thinking, this was the easy part. Now comes the hard part of building the extension, where you have to deal with compilers and linkers and endless error messages. But we actually provide 2 very simple mechanisms for you to build your C++ extension into PyTorch. The first, on the left, uses setup tools, where you write a very short setup.py file, shown here, where you create a CPP extension object, pass it the name and source files of your extension, and when you run setup.py build, we create a Python module for you that exposes your C++ function as a regular Python function. And on the right, we have an even simpler mechanism, which we call just-in-time extensions, where you can actually embed the compilation of your extension into your training script. So when you call torch.utils.cpp extension.load, we will compile the extension for you in the background the first time you call this function, and then basically serve you the resulting Python module on a silver platter. And ultimately, the end result, whether you use setup tools or just-in-time extensions, is that you can import your extension as a Python module alongside Torch, and then use it with PyTorch tensors, PyTorch NN modules, and anything else in PyTorch, even though you wrote your function in C++. And I think that's pretty cool. Now, when you do want to transition from eager PyTorch to TorchScript, you will, of course, want to take your custom C++ or CUDA operations with you. And fortunately, that is very easy. Let's go back to our C++ extension. All we needed to do to bind this into Python were 3 lines of py-11 at the bottom. And to now instead bind the C++ operation into TorchScript for use in your production or inference environments, we just have to change those 3 lines into these 2 lines, where we call torch.jit register operators and tell the torch.jit compiler about our custom operator. And this will allow us to use this custom operation inside TorchScript functions, TorchScript methods, and of course, TorchScript modules, even and more importantly, in the pure C++ serialized format that you'll want to load in your production server. So with a TorchScript, you already saw that you can load your module directly in C++ without any Python dependency. However, at this point, we still expect you to do your training in Python. And that's great, right? We love Python, and if you can use Python, you probably should use Python. However, there are scenarios where you can or want to or need to also use C++ for training. For example, you may want to do a reinforcement learning research for a game like StarCraft or Dota, and are dealing with a high-performance C++ game engine. Integrating Python into such a low-latency, bare metal game engine for such a game would probably be very tricky. So for such scenarios, we're now releasing in beta the C++ frontend, a pure C++ alternative to the Python eager frontend. With the C++ frontend, we aim to provide the aesthetics of PyTorch in pure C++ to enable research in environments that are either low latency, bare metal, heavily multi-threaded, or already written in C++, all domains that are generally tricky to use Python in. So you may be thinking, all right, we gain the ability to train in C++, but what do we lose in terms of the flexibility and aesthetics that Python provides to me? And the answer is actually not that much. Let's take a look. Here on the left, you see the definition of a module in the C++ frontend. And on the right, you see the equivalent definition in the Python frontend. As you can see, they are quite similar. And there are very few differences beyond the syntax of the 2 languages. And the same is true for the training loop. On the left in C++, on the right in Python. And what this means is that if we have to or need to port our Python model from Python to C++, we can do so with very little effort and keep iterating fast. And beyond the similarity in the APIs of the 2 frontends, we also aim to generally keep the architecture and design of the 2 aligned. So on the C++ frontend, we also provide a high-level Torch and then package for neural network functionality. We provide optimizers. We provide data sets and data loaders. We have a serialization format to checkpoint your training. And then beyond that, we also have modules for interoperability between C++ and Python, and C++ and the TorchScript JIT compiler. And that's all I got. Thank you very much. Please do try out the C++ API, the TorchScript custom ops, and the C++ extensions. We have very extensive documentation for these, and please let us know how you like them. Thank you very much.
Hi, everybody. My name is Tang, and actually, I'm a software engineer from Facebook AI Research. So today, I will talk about the distributed training in PyTorch 1.0. And this work is a joint collaboration between Peter from distributed AI team from Facebook and myself. So firstly, I would like to talk about the significance of scalable distributed training. As you all know, compared to the traditional single node, single GPU training, distributed training is basically using more resource in parallel such that the model training can be performed faster. However, distributed training requires a lot of GPU to GPU and host-to-host communication, which is generally very expensive. So if the communication overheads are high, they can easily amortize the benefit and the computation time reduction due to the parallel execution in the distributed training. In other words, your model training will not be scalable. So since the ultimate goal of doing distributed training is basically to significantly reduce the training time by providing great speedups. So that's why enabling scalable distributed training is very important. So reducing the training time not only allows the user to train on more data and the larger models, but this also enables them to do a great amount of model explorations. So therefore, that's why we put a lot of focus on scalable distributed training in PyTorch 1.0. So as you all know, PyTorch distributed functionality is not something new, and we had it for a year since version 0.2. So what is really new in PyTorch 1.0? So the short answer is, it's brand new. In PyTorch 1.0, we designed a brand new performance-driven distributed backend called the C10D library. And this performance-driven distributed library backs up the entire PyTorch distributed functionality, which is from the front-end interfaces to the distributed data parallel. Here are some of the highlights of PyTorch 1.0 distributed. So first, we have brand new backend design. We have redesigned the distributed backend library C10D, and this new library C10D is fully asynchronous, unlike the previous versions. So in the new C10D library, we have provided both Python and C++ support. This is especially useful considering more and more people are now using C++ to train their models. And with this async design, we also make the user API fully backward compatible. The second highlight is highly scalable performance. Scalable distributed training is very, very important, as we talked about earlier. So the scalable performance essentially makes our framework fast. Being fast really means near the roofline performance on the key workloads. And we put a great focus on data parallel performance since it covers many, many use cases. The performance improvements includes both the case of single node, multiple GPU training, as well as multiple node distributed training as well. This is what we're going to talk about later. So now let's take a quick look at the design and feature for C10D library. So the new library backing up distributed is based on 3 backend collective libraries. Glue, which is Facebook's in-house collective library supporting both CPU and GPU. And Nico put a lot of focus on GPU and also MPI. For all the 3 backends we support, we have made all collective calls asynchronous for performance reasons. All collective, both Python and C++, are provided to the user such that the user can simply just use C10D as a library itself if they just want to do distributed training or data transfer. So performance-driven design. We had a lot of performance optimization underneath the user such that the user doesn't have to really take care of the performance optimization. They can just use the library, and the library can provide the performance benefit. What is more, in the upcoming work, we also plan to add fault tolerance and elastic training support to basically get more reliable distributed training. This applies to the case when a node dies, your training can still be ongoing without any sort of interruptions. So as a distributed library itself, this is a native, fully async API we provide to the user on both C++ and Python. Let's take the Python, for example, on the left side. As a user, to use async collectives, all you need to do is create a process group. Can be based on different backend, like process group Glue, process group Nickel, that will perform the collectives. Then you start a couple of collective calls. In this case, it's all-reduce on different tensor, for example. Each all-reduce op will basically return a future as an async op. And all you need to do at the very, very end is to wait on these features. The same applies to the C++ API as well on the right-hand side, as you can see. OK, so even though we designed a new distributed library, fully async, and actually the previous version of torch.distribute is fully synchronous, we still provide a very fully backward compatible torch.distribute API for existing users. In the front-end API, every collective now has an additional parameter called async op that defaults to false. In the default mode, nothing is going to be changed. Then, of course, you can also use the async mode by setting async op to true. What that instead is going to basically return the async op, async worker, then basically wait on that future. Very simple to use. Another optimization highlight we have done for distributed in PyTorch 1.0 is distributed data parallel, which is basically backed up by the C10D library. As we all know, data parallel distributed training covers a lot of the use cases, and we therefore really want to make it fast. Compared to the previous data parallel we implemented in distributed, we have done pretty good performance optimizations. First, as I mentioned earlier, communication is very expensive, and we would really like to amortize it. A very smart way to do it is to overlap it with GPU execution. As you know, as the backward goes through each layer, some of the gradients are going to be available earlier than the others. That's why we can always reduce these, and they can potentially overlap with further backward computation. Second, there are many gradients to be sent over the network, and some of them are really small. Therefore, we coalesce them into a big tensor before sending them to basically reduce the number of all-reduce operations that can potentially improve the performance. As you see at the bottom, the bottom graph shows the actual NVIDIA visual profiler timeline. This is for ImageNet. So as you can see, stream 21, which is a dedicated Nickel CUDA stream that is actually managed by C10D library. And we can see completely overlapping between the Nickel all-reduce kernels and actually the backward kernel in the default stream. And due to the default of 25 megabytes of bucket we implemented in data parallel, the number of all-reduced kernels is only a few instead of many. So this basically shows the two-sort optimization reflecting in the profiler. Now let's take a quick look at the performance, which is really what we care about. I will first talk about the single-node performance, because it's actually the baseline. So the single-node distributed training is currently the fastest way to train on a single node with multiple GPUs using data parallel. So imagine you have one node with 8 GPUs. Instead, you can basically launch like 8 processes, and each process is going to work on a single GPU and do distributed training. So since PyTorch 0.3, fast single-node distributed training is not possible, and people will generally use data parallel module, which achieves 2,700 images per second for ResNet 50 on one single DGX1 node with NVIDIA 8X V100 GPUs. This is only 81% of the efficiency, which is not good. In PyTorch 0.4, we added a faster single-node distributed training using the Nickel backend of the distributed library. And this brings the perf to 3,200 images per second. And this actually is the IP32 as well. And this is already at the 97% of efficiency. In PyTorch 1.0, with the new backend, brand new design, we maintain the same performance at 97% of efficiency. What this really, really means to the user is that there's only 3% of the communication overhead involved with 8 GPUs compared to 1. So as the single node performance near the roofline, for single node training with very fast NVLink inter-GPU connections, you might not be able to see a huge performance gain. However, if the training is done on host with slower inter-GPU connect, like PCI Express, you might see some sort of performance improvement due to the communication overlapping, as we talked about earlier. With a very close to roofline single node baseline, now let's take a look at the scalability of multiple nodes. First, let's take a look at example for ImageNet ResNet 101, a vision model. This diagram shows the speedups compared to the single node performance by scaling the number of nodes from 1 to 8. And the green bar shows ideal speedup. For the 8 node, actually the ideal speedup is going to be 8. We here demonstrate 2 kind of hardware network configs. So basically, every node is a 8x V100 host interconnected with either 4 100 gigabits of InfiniBand or one single Ethernet with 100 gigabits of Ethernet as well. So as this shows, it scales pretty well. In the case of 8 nodes, 64 GPUs, we have about 7.5 speedups and 5% of communication overheads for the case of InfiniBand. And for the case of Ethernet, it still linearly scales pretty well and achieves 7.2 times of the speedup and 10% of the communication overhead. Another example will be FairSeq, which is a sequence-to-sequence model, machine translation model developed by Facebook AI Research. The left figure shows a similar sort of speedups results from 1 to 8 nodes. As we can see, it scales pretty well, and with over 6x speedup with 8 nodes. You might wonder why it doesn't scale not as linearly as the previous model. The reason is that FairSeq is a much, much larger model that has a lot more data to be transferred over the wire. The second one is uneven batch size, which basically means the worker can get different batch size due to the nature of the model itself, and the performance is basically limited by the slowest worker because it has to do the asynchronous communication at the very end. So the right figure shows a training time reduction. So going from 1 to 16 DGX1 node brings the total training time from 5 hours to half an hour, which is really amazing. And this is about 19% of performance gain when we switch to C10D DDP, distributed data parallel, for FairSeq, thanks to the overlapping optimization we have done. So Michael will have a talk about FairSeq later, can provide more details. So OK, where can you find all these? So all these new features distributed on PyTorch master were on the nightly builds. So the old torch.distributed API are now deprecated to torch.distributed.deprecated. So this pretty much covers the highlights of the distributed in PyTorch 1.0, and thank you.
So we're going to take a short break. Be back here at 10:55. In the meantime, shameless plug for the community. So Dilip and Brian have a new book coming out in January, but I think you can pre-order it now. So NLP on PyTorch. So see you guys in about 15, 20 minutes. Thanks.
Compared to 1. So as the single node performance near the roofline, for single node training with very fast NVLink inter-GPU connections, you might not able to see a huge performance gain. However, if the training is done on hosts with slower inter-GPU connect, like PCI Express, you might see some sort of performance improvement due to the communication overlapping, as we talked about earlier. With a very close to roofline single node baseline, now let's take a look at the scalability of multiple nodes. First, let's take a look at example for ImageNet ResNet 101, a vision model. This diagram shows the speedups compared to the single node performance by scaling the number of nodes from 1 to 8. And the green bar shows ideal speedup. For the 8 node, actually the ideal speedup is going to be 8. We here demonstrated 2 kind of hardware network configs. So basically, every node is an 8x V100 host interconnected with either 4 100 gigabits of InfiniBand or one single Ethernet with 100 gigabits of Ethernet as well. So as this shows, it scales pretty well. In the case of 8 nodes, 64 GPUs, we have about 7.5 speedups and 5% of communication overheads for the case of InfiniBand. And for the case of Ethernet, it still linearly scales pretty well and achieves 7.2 times of the speedup and 10% of the communication overhead. Another example will be FairSeq, which is a sequence-to-sequence model machine translation model developed by Facebook AI research. The left figure shows a similar sort of speedups results from 1 to 8 nodes. As we can see, it scales pretty well, and with over 6x speedup with 8 nodes. You might wonder why it doesn't scale not as linearly as the previous model. The reason is that FairSeq is a much, much larger model that has a lot more data to be transferred over the wire. The second one is uneven batch size, which basically means the worker can get different batch size due to the nature of the model itself, and the performance is basically limited by the slowest worker because it has to do the asynchronous communication at the very end. So the right figure shows a training time reduction. So going from 1 to 16 DGX1 node brings the total training time from 5 hours to half an hour, which is really amazing. And this is about 19% of performance gain when we switch to C10D DDP, distributed data parallel, for FairSeq, thanks to the overlapping optimization we have done. So Michael will have a talk about FairSeq later, can provide more details. So OK, where can you find all these? So all these new features distributed on PyTorch master were on the nightly builds. So the old torch.distributed API are now deprecated to torch.distributed.deprecated. So this pretty much covers the highlights of the distributed in PyTorch 1.0. And thank you.
So we're going to take a short break. Be back here at 10:55. In the meantime, shameless plug for the community. So Dilip and Brian have a new book coming out in January, but I think you can pre-order it now. So NLP on PyTorch. So see you guys in about 15, 20 minutes. Thanks.